In this class, we will discuss about one of the applications of Bernoulli's theorem, a device known as Venturimeter, which was developed by the scientist Venturi. So, this Venturimeter is used to measure the flow in pipes. Suppose if you want to measure the discharge in a pipe with some diameter, you can always find out by fitting a Venturimeter into the pipe. It works under the principle of Bernoulli. So, Bernoulli theorem, which I have explained in the earlier lecture, that is used as a basic principle for the development of this Venturimeter. And it can be inserted to a horizontal pipe or an inclined pipe or a vertical pipe also. Now, this is the typical sketch of a Venturimeter. You have a pipe here. So, this is the pipe with some diameter d1. So, d1 is the diameter of this pipe. To this pipe, a Venturimeter is fitted. Venturimeter consists of three parts, three components you can say. It starts from here. So, you have a converging cone portion here over this length. Then you have a throat section where the diameter is constant. In the converging cone, you have the diameter reducing. Then in the throat section, diameter is constant. Then you have diverging cone. In this diverging cone, you have increasing diameter. And of course, the diverging cone at the end, you have the diameter equal to the diameter of the pipe itself, d1. So, diameter of the throat, we can take it as d2. So, this diameter is d2. So, d1 is the diameter of the pipe or diameter of inlet of the Venturimeter, and d2 is the diameter of the throat section. So, you have converging cone, throat section and diverging cone. And the angles, subtended angle of this converging cone, I have denoted as alpha 1. This alpha 1 can be normally 21 plus or minus 1 degree. That means it can be 20 degree or 22 degree. Or it can be 21 degree also. So, plus or minus means it can, the minimum maximum values are 20 and 19 and 22, like that you can take. Then 20 and 22 you can take. Now, alpha to this value, this triangle, normally it is 5 degrees. And the length of this diverging cone section, diverging cone, so this will be approximately 2.7 times d1 minus d2, diameter at inlet and diameter at throat. Then d2 is normally 0.5 to 0.6 times d1. So these are some of the basic geometrical dimensions of this Venturimeter. Of course, they have been arrived at by doing some experiments. Now, here one is the inlet section, this is the inlet section, 2 is the throat section. So, to these two, at these two sections, a U-tube differential manometer, so this is the U-tube differential manometer, it is attached. So, the purpose of attaching U-tube differential manometer is to measure the pressure difference between these 2 points. So, if P1 is the pressure here, P2 is the pressure here, P1 minus P2, we have to find out. Here, always the pressure at the inlet section will be more than the pressure at the throat section. I will tell you why. Some fluid is flowing through this pipe with some discharge Q. Specific weight of that particular fluid is gamma. So, when the fluid enters in this direction, this is the direction of flow. Direction of flow is this with some constant discharge. I am going to take the rate of flow as steady discharge, that is constant discharge. You can observe here that d1 is greater than d2, diameter at inlet is greater than diameter at throat. Therefore, naturally, A1 will be greater than A2, cross-sectional area of flow at inlet will be greater than cross-sectional area of flow at throat. Since A1 is greater than A2, V1 should be less than V2 because we know that Q is equal to A1, V1 is equal to A2, V2, continuity equation. So, where the area is more, velocity will be less to have the same discharge. When V1 is less than V2, P1 should be greater than P2 according to Bernoulli's theorem, which I have explained in the last lecture. So, because of this equation, we can see here, since the sum is constant, if P1 is greater than P2, naturally V1 should be less than V2. So, these are the things. Now, what we have to do is we have to apply the Bernoulli's equation between the sections 1 and 2. So what I am doing here is I am going to derive an equation for the rate of flow or discharge through this Venturimeter. So if you want to find the flow rate in the pipe, you can attach a Venturimeter by measuring the pressure difference between the inlet section and the throat section. You can always compute the discharge. So that means there is a specific relation between the discharge and the pressure difference. Now let us see how we can derive it. If you apply the Bernoulli's equation between the sections 1 and 2, so this is the Bernoulli's equation and assume no losses. So that means your HL value will be 0. We can assume no losses. When you are assuming no losses, we are getting a theoretical value of discharge. Q theoretical, we say. But actually, in practice, there will be some loss during the flow, maybe frictional loss, any other losses. Due to that, your actual discharge will be slightly less than the theoretical discharge. That means, if you are neglecting losses, you are going to get theoretical discharge expression. If you are assuming discharge, if you are assuming the loss, then you are going to get the actual discharge. So, assuming losses, you are going to get actual discharge. Neglecting losses, you are going to get the theoretical discharge. Now, if you write the expression of Bernoulli's equation, at section 1, the total head is P1 by gamma plus V1 square by 2G plus Z1. And at section 2, the total head is P2 by gamma plus V2 square by 2G plus Z2 plus losses HL. So, HL is the loss. Here, I am going to take this loss as 0, and if you observe the sketch here, I have taken a horizontal Venturimeter. So, the pipe is horizontal, therefore, Venturimeter setup also is horizontal. In such a case, if I take the center line of the pipe or center line of the Venturimeter itself as datum, you can see here, this itself as the datum, then both Z1 and Z2 values will be 0. So, that means these two will get cancelled. Now, the equation reduces to this form. Because Z1, Z2 they are 0, HL is 0. So, you will get P1 by gamma plus V1 square by 2G is equal to P2 by gamma plus V2 square by 2G. Now, rearranging the terms, P1 minus P2 divided by gamma, because gamma is common here. This will be equal to 1 by 2G. If you bring to that side, V2 square minus V1 square. This term 1 by 2G into V2 square minus V1 square, which is equal to P1 minus P2 by gamma. This term is called as the Venturi head. Very important, Venturi head, capital H. So this will be in meters. Venturi head value will be meters, capital H. This I called as equation 1. Now, as already told, the pipe is carrying a constant discharge, a steady discharge, which is Q. So that means by continuing the equation, Q is equal to A1V1 is equal to A2V2. This I have told in the earlier classes. So if you use this equation, so what you can write here is V1 is equal to Q by A1 and V2 is equal to Q by A2. Now in this equation 1, just I will try to write in another form. So H is equal to 1 by 2G into V2 square minus V1 square, or V2 square minus V1 square will be equal to 2GH. If you bring to that side, it becomes 2GH. Now what I will do is I will substitute for both V1 and V2 as Q by A1 and Q by A2 in this equation. So you will get Q by A2 whole square minus Q by A2 whole square, A1 whole square is equal to 2GH. So this, if I rearrange the terms and if I simplify, you are going to get Q is equal to, because Q is the unknown here, I want to find the discharge through the Venturimeter or through the pipe. You are going to get Q as, so root 2GH divided by root of 1 over A2 square minus 1 over A1 square. If you take the LCM and if you simplify, you are going to get an expression like this. A1 A2 divided by root of A1 square minus A2 square into root 2GH. So this is the equation of discharge. Since here I have not considered any losses, when you are deriving the equation, I have taken HL is equal to 0. This equation gives theoretical discharge. So QT value this will give, because we are assuming no losses. So therefore QT is equal to A1 A2 divided by root of A1 square minus A2 square into root 2GH. Here A1 is the area of flow at inlet, that is the area of the pipe itself. A2 is the area at the throat section, and H is the Venturi head, which is given by this P1 minus P2 by gamma. So this is how we can get the expression. Now if the losses are considered, then the discharge becomes the actual discharge. So if you want to include that, if you want to find the actual discharge, then we have to multiply the theoretical discharge by a coefficient called coefficient of discharge. So this coefficient of discharge, this will account for the losses. Normally in the case of Venturimeter, the value of CD, which is denoted as CD, coefficient of discharge, varies from 0.9 to 0.98. The meaning of that is, if the value of CD is 0.9, then 10% losses will exist. If the value is 0.98, 2% losses are there. So 1 minus that value gives the percentage of losses. So now if you want the actual discharge, so Q actual is equal to, see, you have to include CD here, CD into Q theoretical is this value. So CD into A1, A2 root 2 divided by root of A1 square minus A2 square. So this is called as the discharge equation of Venturimeter. So this is called as the discharge equation of Venturimeter. So they may ask you to prove this. So you have to draw the diagram. We are using two important equations. One is the continuity equation, Q is equal to A1, V1 is equal to A2, V2. Another one is the Bernoulli's equation, P1 by gamma plus V1 square by 2 is equal to P2 by gamma plus V2 square by 2. By using these two equations, you can derive the discharge equation through Venturimeter. So this is the discharge equation. Here, CD is constant, A1, A2, root 2G. So up to this it is constant. So what I can do here is, this entire thing, CD into A1, A2 divided by root of A1 square minus A2 square into root 2G, I can take it as another constant K, which is called as Venturimeter constant. So if you take that as K, then Q actual is equal to K into root H, because this entire thing is K into root H. So that means discharge is directly proportional to H to the power of half, because QA is equal to K into root H. So if you remove the equality sign, if you want to introduce variation sign, Q directly varies with H to the power of half. So this is the discharge equation for a Venturimeter. Now here in the diagram you can see here, the pressure at in the inlet is more, pressure at throat is less. That's why I have taken the mercury level lower here, because this exerts more pressure. Here pressure is less, therefore mercury level will be lower at the limb, in the limb which is connected to inlet section, and it will be higher in the limb which is connected to throat section. This whatever deflection is there in the mercury level, that we can read out in the experiment. So I have taken gamma as a specimen of the fluid flowing here. Now next what we can do here is, we can always get an expression which relates this capital H and small h. So capital H is Venturi head, small h is the deflection in the mercury levels in the manometer, which is connected to the inlet and throat section. Now in any problem, so sometimes you will be asked to find out the deflection level of mercury in the manometer. They may give other data. Then how to do that? So now for that, what we will do here is, we will derive the relationship between capital H and small h. So capital H is the Venturi head, small h is the deflection in the mercury level. So this capital H is nothing but P1 minus P2 divided by gamma. This is capital H. Okay. Now I will just derive relation between capital H and small h. Capital H is the Venturi head, small h is the deflection in the mercury levels in the manometer. So for that, to get that, I have to go for the gauge equation. Now I will consider 2 points here, that is 1 and 2. These two are the points to which this manometer is connected. So this is how, I will just only write the manometer setup here. So it will be something like this. So from the same diagram, I am taking this manometer sketch separately. So here I have taken mercury level here and mercury level here. So these two, 1 and 2 are the same level. Okay. So this distance, this I will take it as A, this side take it as B. So this is the mercury. So what I do here is, so this is mercury. I will take the specific gravity of this mercury as S2, and whatever water is flowing, well, not water, any liquid may be flowing in the Venturimeter. I will take the specific gravity of that liquid, whatever is flowing in the liquid in the Venturimeter as S1. So S1 is the specific gravity of the liquid flowing in the Venturimeter or pipe, and S2 is the specific gravity of the monometric liquid, and this is H. This is H. Now I want to get a relationship between capital H and small h. So for that we have to write the gauge equation. I have explained you how to write the gauge equation in the earlier classes. So what I do here is, here from here to here, I will take from here to here, I will take it as x. Now if you want to write the gauge equation in terms of meters of water. I have told you that because water is the reference liquid. Gauge equation in terms of meters, that is pressure head, meters of water, because two different liquids are there. Some liquid S1 and mercury S2. How to write the gauge equation? I have explained that. Start from point 1. So P1 by gamma W. So this is the pressure head at 1 in terms of water. Then this A is below this 1. So what I have to do here is, I have to take this total length, which is x plus h. You can see here, this is x plus, x is from here to here, 2 to B, and h is from B to A. Therefore, it is x plus h here. Since point A is below point 1, then your pressure is more. Therefore, plus sign you have to take. Elevation difference is x plus h into specific gravity of the liquid contained between 1 and A, which is S1. So this I have explained in the earlier lectures. Please go through that. Then from A to B is above A, therefore pressure is less, minus we have to take. H is the difference, vertical difference between A and B, elevation difference between A and B, into specific gravity of the liquid which is there between A and B is mercury, that is S2 I will take. So then I will have to go to point 2 there. Once again 2 is above B, therefore pressure is less. So minus distance, vertical distance between 2 and B is x, into the liquid contained here has got a specific gravity of S1, and this should be equal to, so P2 by gamma W. So this is how we have to write the gauge equation. This I have explained in the earlier lectures. Please go through that. Now here we have to simplify this. Let me simplify this now. P1 minus P2 by gamma W. See, I have brought this to this side is equal to, all these terms I will take that side, minus x plus h into S1 plus h into S2 plus x into S1. Now if you simplify this, minus x into S1 plus x into x1 will get cancelled. So you will be left with h into minus h into S1 plus h into S2, or you can write it as h into S2 minus S1. So this is what you get. Now after this, what you can, now suppose if now I have introduced water here, gamma W here, but if I want in terms of the equation in terms of the flowing fluid specific weight is gamma. So now what I have to do here is, we know that gamma of the flowing fluid is equal to specific gravity of the flowing fluid multiplied by specific weight of water. So this is from the definition. Now what I will do here is, so if I substitute this for gamma W, you can write it as gamma divided by S1. Now if I substitute for gamma W as gamma divided by S1, so this equation becomes now P1 minus P2 divided by gamma by S1 will be equal to H into S2 minus S1. All this S1 goes to numerator here. So what happens? S1 into P1 minus P2 divided by gamma will be equal to H into S2 minus S1. Now you can see here P1 minus P2 gamma is nothing but capital H. Please understand here. P1 minus P2 by gamma is equal to capital H. Therefore, S1 into capital H is equal to H into S2 minus S1, or you can write H is equal to small h is equal to capital H into S1 divided by S2 minus S1. So this is the relationship between the reflection of mercury in the manometer, that is small h, and the Venturi head capital H. Now this one you can apply. Suppose if the flowing fluid is water, if flowing liquid is water, then what happens? So S1 value will be 1, S1 will be SW, that will be 1, and if the manometer liquid is mercury, then S2 will be 13.6 for mercury. Then if you substitute that here, H is equal to capital H into S1 is 1 divided by 13.6 minus 1, or in other words you can write H is equal to capital H is equal to 12.6 times small h. So this is another way. That means if you know the deflection in the mercury level small h here in the manometer, just by multiplying by 12.6 you are going to get the value of Venturi head if it is water and mercury. Please note that S1 is 1, S2 is 13.6 if it is a combination of water and mercury. If it is some other liquid, then we have to use this expression to get the relationship between H and H. So if it is other liquid, then here if you see capital H will be small h into S2 minus S1 divided by S1. So suppose if it is oil, some oil is flowing with specific gravity 0.9, and this is mercury, manometer liquid is mercury, then in that case S2 is 13.6, S1 will be 0.9, here also S1 will be 0.9, that we are going to get the corresponding relationship between capital H and small h. Once this capital H is known, then using this equation you can find out the actual discharge. So CD into A1 A2 divided by root of A1 square minus A2 square into root 2GH. So once this capital H is known, by substituting here you can find out the actual discharge, or if they give the discharge value you can find out CD value. So CD value normally for a Venturimeter standard value lies between 0.9 and 0.98. That means if the value is high, if CD value is high, its discharge capacity is more. That is the meaning. That means only 2% losses will take place during the flow. If the CD value is low, more losses will be there.